Hello. Okay. Hello, everyone. Welcome to both Eat Belgrade and also this talk. Quite appreciate it. As he presented me well, I'm working at Inco as a researcher coming from mathematics and cryptography background. And today, I will try to explain our collaborative work with Circle Research on confidential ERC20s, leveraging fully homomorphic encryption. So, yeah, transparency has been a feature in Web3. Everything is public, everything is traceable, good. But for us, it's also a problem because I think without a certain level of privacy, it's almost impossible to achieve the goal of mass adoption. And that's why we're trying to bring privacy in a hopefully compliant manner to Web3. One other thing, too, I think it's worth distinguishing and being aware of is the difference between confidentiality and anonymity. Confidentiality is actually way more, I think, promising and also quite important because in anonymity we have several problems we have faced in the Tornado Cash stuff and the other alternatives in privacy space. But by confidentiality, our goal is to bring privacy into Web3 in a hopefully compliant way. And I think this is that formula to bring the mass adoption. So what I mean by compliant privacy, I mean is transparent, both keeping the transparency, traceability in a private manner. For instance, assume you're going to make a transfer and your address is public, probably written on your Twitter profile in the ENS form, and I'm sure you don't want to expose your transfers, your investments in DeFi, and the other stuff related to your money. And I think the starting point to discuss privacy is a question, and I think that is what actually people don't want to reveal. And probably the first answer is money. By money, what I mean is the salaries, transfers, investments, and anything about finance, and in both personal and also institutional manner. The other answers could probably be healthcare, which is quite out of the scope of this talk, but I'm also quite interested in that part, and I would love to discuss any of you if you're interested as well in the venue. So if money is one of the key things that people want to hide and are not willing to reveal about any aspect, then, and also if blockchain technology is one of the revolutionizing ways of decentralizing money, then why not combining these two? This was actually the starting point where people started thinking about bringing privacy into Web3. And different privacy solutions existed so far: Tornado Cash, Zcash, and any other solutions were there. They're still there, but everything has its own trade-offs. And the other thing, which I think is important to discuss and be aware of the distinctions, is what we call commitment versus encryption. So commitment-based privacy is also possible by using simply ZK or other primitives, but there is also an encryption-based approach to achieve privacy. So in this chart, we simply compare commitment versus encryption approaches to bring privacy. In terms of compute overhead, obviously, FHE by its own nature, and also the fact that it's still a baby right now, it's fairly new technology. It's compute heavy, but this heaviness lays in the server part. In our case, blockchains on the blockchain. But in the commitment-based approaches, the compute heaviness actually lies in the client side because proof generations mostly run on the client side. In terms of privacy, commitment-based approaches probably have more privacy. like especially in the cases where in the cases like Tornado Cash and the others. But this is also, even though I'm not a big fan of compliance, this is a reality for both like our future and also the mass adoption strategy of Web3 and the ecosystem partners. And like it's also possible to make it more private, but that wouldn't be great for compliance-related things. Yes, and this is our work with Circle Research and Inco. We call it Confidential ERC20 Framework. It is based on FHE. It's also possible to achieve confidential ERC20s with different ways, like TEs also as well. But I mean, as always, each has its own trade-offs. We have simply like mainly two, but optionally 3 contracts. The main confidential ERC20 contract is actually really, really similar to the regular ERC20 contracts. But the main difference is, which I'm also going to extend in upcoming slides, we implement encrypted types and encrypted inputs. For instance, like mappings like balances, allowances, or like functions like mint, burn, transfer are done homomorphically, which allows us to build this contract. The wrapper contract actually is a part of the UX. It simply takes as input a regular ERC20 token, USDC or something else, and wraps it into its confidential equivalent, and vice versa. Possibly, it's also possible to build a compliant confidential ERC20 contract, obviously, which would allow mostly governments to blacklist someone or like define some ACL, access control list as a condition. But obviously, this is the topic of future. So what is FHE? I love to talk about FHE, and like it's probably a million times that I'm talking about FHE, and I want it to be talked more than we have right now. It stands for fully homomorphic encryption, and the main difference between the other encryption schemes is it actually allows you to compute on encrypted data. Normally, in other encryption schemes like elliptic curve-based, RSA, different stuff, we have many different schemes, symmetric ones, asymmetric ones. They simply use a or more than one key to encrypt or decrypt a plain text or ciphertext message. And the goal here is to protect the confidentiality of the message while transfer or storage. But sorry, but they don't allow you to do any operation on top of the ciphertext. Why this is important? For instance, like big servers stores dozens of data, petabytes of data, also blockchains, it's the same. We have many data stored or being transferred, but till 2009, it wasn't possible to perform like computations on ciphertexts or encrypted data. But in 2009, Craig Gentry from, it was Stanford, if I'm not wrong, proposed the idea, like the first actually theoretically working fully homomorphic encryption scheme. It was based on lattice-based cryptography and ring learning with error ciphertexts. But obviously, it was almost impossible to implement from the performance perspective. Since 2009, we have developed many different schemes. Some of them are leveled, some of them are non-leveled. Leveled ones are mostly, when you compute on that, the level of noise, which we call as that way, some kind of mathematical error grows, and you need to find a way to reduce the error, actually. And that was the reason why we couldn't achieve a fully homomorphic encryption scheme till 2009. But recently, actually, FHE schemes improved quite well from the performance perspective, but obviously, it's not still super great to use in our daily lives. But it's actually suitable to build a confidential token on a blockchain. As I said, there are many different schemes. FHE is one of them. It is fully homomorphic encryption over the torus. You can Google it that way. And the next question as a blockchain person is how to apply FHE on blockchains, or particularly EVM. It's simply, there are two ways. Like, we can make it natively as adding a precompile to the main EVM code, but that would be that would be not that efficient, considering that even 256 R1 curve isn't implemented. I mean, even I wouldn't want the FHE precompiles to be added into EVM because they are huge. So the other way is the co-processor approach, which is actually utilizing a different L1 and corresponding contracts on what we call host chains. It could be Ethereum mainnet itself or other L2s. And that way, when you want to build a confidential smart contract, what you actually need to do is to interact with the co-processor contract to allow the usage of encrypted types and encrypted inputs. So what are these encrypted types? They are actually quite similar what we currently have in Solidity. So we have uints, we have uints, booleans, addresses, and stuff. And thanks to FHE library, now we have EUINT, standing for encrypted uint, encrypted boolean, and encrypted addresses. In addition to these types, we need to have some methods or functions because, I mean, that's the entire thing, like being able to compute on ciphertext. Similarly, we have like tfhe.add, subtract, multiply, divide, or some comparison operations like greater than or equal to, and things like that. Note that as it's fully homomorphic, you can do literally everything on ciphertext. But I cannot promise about performance yet. But in terms of confidential tokens and blockchain setup, it works quite well. How about trust assumptions? The main trust assumption would be the usage of ZK. We need to use ZK because in a fully homomorphic encryption-enabled EVM, or FHE EVM, users will be the ones who provide ciphertext to the blockchain, right? But we need to check if those ciphertexts are well-formed, because otherwise that would break the other ciphertext that's gonna interact with. And the other thing, we also need to check if the user submitting the ciphertext knows the underlying plaintext. So these, what we call them is ZK-POK, zero knowledge proof of knowledge. And that ZK proof simply has two aspects, like the submitter knows the underlying plaintext, and also the ciphertext is indeed well-formed. In the blockchain setup, how is decryption performed? Decryption is simply an MPC setup. Because like the key that we use to encrypt is a global public key, so everyone knows it. So when a person A wants to encrypt, they use the global key, or another person B, when they want to encrypt, they use the global public key. So decryption key is also the same for everyone, but no one has it, and no one should not have it, because otherwise, everyone will be able to decrypt the other people's ciphertext. So the solution is to use something we call like linear secret sharing scheme built by Zama researchers. Simply, it's a secret sharing scheme to split the decryption key along the validators, and when someone requests a decryption and they prove the ownership of that encrypted data, then the threshold network runs, and if 66% of the network agrees on the fact that, okay, this person has a right to decrypt the ciphertext, then the threshold decryption works and the user gets its data. And yeah, this is an example of a confidential transfer. As you can notice, the balances mapping has a really small difference than the regular one. The mapping is defined from address to EUINT instead of a UINT. So the mapping will look like, in the first column there will be addresses, and in the second column there will be gibberish ciphertexts. And no one will be able to read it without permission or without having the right to decrypt it. The transfer function, we have obviously a conditional. The can transfer Boolean. It's also encrypted, and it simply compares the amount and the balance of the sender. And this is also should be familiar from the regular ERC20. And then simply updating the from balance and to balance is done homomorphically by using FHE.add instead of a regular plus and equal signs to perform the addition. And this is from the viewership. I'm going to skip this. And yes, composability is a really important feature, comes with FHE, instead of using a commitment-based approach. Because normally, let's assume you build a confidential token, and your friends build a privacy-preserving decentralized application. These two separate things will interact really smoothly without needing to make them aligned in some manner. And this is actually naturally enabling shared private states. I wouldn't say this is the perfect solution, but I would say for most cases, it's one of the most promising solutions in terms of privacy. We have also the thing we call programmable decryption, and that's also something related with the compliance side of the case. And it's also possible that in the contract creation level, the creator of the contract would grant some sort of extra access to some parties. Obviously, this is not needed. This is something extra just to avoid legal problems. But yeah, this is also possible. But even though, as I said, I'm not a fan of this legal things related with compliance, I have to admit it's kind of needed for the mass adoption. Programmable transfer rules, this is also something I really like. You can define some rules for transfers, and you can treat it as something as automated in the workflow. It could be about salaries being paid in every single day of each month, or it could be something else. So beyond this, what kind of use cases we have? We have private cross-border payments, private token vesting, private B2B payroll, private even salary level payroll. Also, in terms of DeFi, almost everything is possible, like private AMMs, dark pools, real-world asset tokenizations, blind auction, and private lending. And I'm sure there are some teams working on several of these. Yeah, to conclude, confidential ERC20 framework offers a balance between privacy and usability and developer experience because it's pure solidity with extra data types and methods. So no need to learn a new language or new developer setup. And it's composable. You can build something that is going to work really well with different privacy-preserving applications or tokens or, anything you can imagine. So yeah, we're quite excited about this. And if you want to quite dive deeper into the technical details, you can take a look at the research paper itself. I think it's a good one. And I hope you like this presentation. Thank you so much.
Okay, thank you, Furkan, for the talk. Do we have any questions? There's one there.
I noticed in the confidential ERC transfer function that address is not encrypted.
Yes.
Could it be encrypted?
Yeah, totally. But it would need or require extra logic within the transfer function to, actually prove if it's a legit, not legit, but it would be harder to, let's say, require the first require line, and that's why in the first place we wanted it to be as simple as possible and only encrypting the transferred amount or minted amount or burned amount. But it's also possible, yes.
Thank you.
Sure.
Any other any other questions?
Yeah.
Yes, no. Let's give Furkan an applause.